this second chapter of trigonometry, we were going to be extending our knowledge of the trig functions. In this lesson, we will be looking at trigonometric functions and their graphs.
Hello, so for the next few minutes here, we're going to take a look at something called periodic or sinusoidal functions. Okay. Now, the essence of what's going on here is basically this. Let's talk about the sine function for right now, just the sine function. When you take your terminal arm, okay, and drop it along the positive x-axis here, okay, remember sine is related to the y-coordinate, okay? As we go along the unit circle, the sine is related to the y-coordinate. So right here, it's 0, and then it increases, okay, it goes like, you know, a half, root 2 over 2, root 3 over 2, then it goes to 1, root 3 over 2, root 2 over 2, a half, and then it comes down to 0, and then it goes down to negative, and it does all of that, goes through the same cycle down here to -1, and then it comes back up to +1, straight to 0, I should say. And then once it hits here, once it's gone around a full 360, it does the whole thing over again. It goes through the exact same set of values here. When you get a function that does that sort of thing, where it goes through the same values over and over again, kind of repeats this little pattern here, we call it periodic. Okay, the period being specifically I want to say the amount of time, but like the distance between the parts of the graph that are repeated. So in this case here, for example, a sine function repeats after 360 degrees. So the period here would be, in this case, 360 degrees or 2 pi radians, okay? Because that's when these things repeat. Now, we also call them sinusoidal functions, and you're going to see in just a couple seconds here why we do that. But a sine function has a very, very specific sort of graph, very, very characteristic graph, and we call that kind of a graph a sinusoidal graph, and anything that kind of behaves like that is called sinusoidal. We'll take a look at that in just a second.
The sine function. And we'll start with y equals positive sine x.
So the first thing we're going to do is take a look at the sine function, because it's the one that it's actually named after, the sinusoidal functions here. So on my scale here, I'm going to put the angles along the x-axis, and I'm going to put the values of sine along the y-axis. And I know that I'm going to get up to 1, and I'm going to go down to -1. Notice that on my scale here, this is 90 degrees here, so that means each one of these little lines is going up by 30 degrees. I'm just going to help myself with a bit of a scale here. This is going to be a half. Down here, this is going to be -1/2. And then for sine, I know that sine of 60 degrees is going to be root 3 over 2. That's going to be quite high. It's going to be somewhere up here, root 3 over 2, and then down here you're going to have your negative root 3 over 2. So here we go. So at 0 degrees, sine is 0. 30 degrees, it's going to be a half. That's going to be up here at root 3 over 2. 90 comes back down to a half, and then 0 at 180. Then, just as I go over here, that little bit right there kind of repeats, but down here in the negative portion, so it's going to be down here, here, there, and then to 360. And when I connect these dots, I get this nice curve. Looks something like that. Actually, that's pretty good. And that's what the sine graph looks like. And it's got this nice little wave portion to it. Okay, in fact, anything that has kind of a wave nature to it is typically going to be modeled with a sinusoidal graph, like a sine graph here. Now notice that this is going to continue on. Okay, and if I was to go backwards here, here's -90. This would go down to here, and then negative. So this thing would drop back down like this. So it repeats in both directions here. Okay, it goes forward and backward, covering all real numbers. Okay, a couple things about the sine function else that I want to mention here. Notice that it can actually be broken up into 4 different motions. Okay, the sine graph starts at the center of its motion. Okay, if you look at this thing and draw a couple horizontal lines like this, a sine graph starts at its middle and then goes up. Now notice what happens here. It goes up till it hits 90 degrees. Now think about that. 90 degrees up here. Let's relate it to, whoops, wrong way. Let's relate it to this thing. From 0 degrees to 90 degrees, hey, this is the first quadrant. Sine is positive and increasing. Then from 90 degrees to 180 degrees, again, still positive, but now the values are decreasing. Then from 180 degrees to 270 degrees, okay, it's negative and it's decreasing. So here's our third quadrant. And then it hits -1, and then from 270 to 360, okay, we're in the fourth quadrant. And what's happening is it hits its negative, its minimum here, and then it increases to 0 in that fourth quadrant here. So what we can do here is we can take this sinusoidal graph and break it into the four quarters, 4 different motions, okay, and those represent the 4 different quadrants. You need all 4 of these for a complete period of pi, okay? So this distance right here is the period from 0 to 360. Once I get past that, this piece repeats. Okay, if I go backwards, that piece repeats. But the amount of time it takes to repeat is 360. Okay, it's got to run through its positive values, its negative. Basically, it's got to run through all 4 quadrants. Think of it like that. It's got to run through all 4 quadrants in order for it to repeat.
And now we'll look at y equals negative sine x.
Okay, now we're going to take a quick look at y equals negative sine of x. Now, there's so much beautiful overlap here in the mathematics, and you already should be aware of what is going on when you throw a negative in front of the function. Okay, a negative in front, just like it did in Math 20 with parabolas, in the transformations chapter that we did a while ago here, the negative causes a vertical reflection over the x-axis. So it's going to look, the shape is going to stay the same. We are going to maintain the shape of the sine graph. It's just going to move in an opposite direction here. So now I'm going to put my little scale on here again. So here's my 1/2, -1/2, then out here, negative root 3 over 2. This will be positive 1/2 up here, positive root 3 over 2. But this time, because of the negative sign, instead of going up and then down again, this is going to actually go down first. And then it's going to start to come back up. Then it's going to, when we pass 180, then we move into the positive rotation here. So it's going to go there, there, the 1/2, and then down to 360. So now, draw it like this. Yeah, well, that's not great, but anyway, you get the idea. This is what negative sine looks like. And again, we can split this thing up into its 4 different quadrants. Okay, and notice the motions here: down to the minimum, up to the middle, up to the maximum, down to the middle. Okay, you need those 4 different motions here to create a full period here. You need to be sliding through all 4 quadrants in order to get this thing to have a full period. So again, the period is 360. That negative there, putting it in front there, didn't change anything. Once again, these functions, okay, can be extended left and right here. Okay, so the domain continues to be all reals. Again, all we've done in this case is flip it. Notice that it's still starting. If you draw those horizontal lines right there, okay, the negative sine graph still starts right here. The first quadrant begins on the origin, at the middle of its motion here. Now, it's not always going to start at the origin, but it will always start at the middle of its motion here, this vertical motion.
The cosine function. And again, we'll start with y equals positive cosine of x.
Okay, now we're going to take a quick look at cosine. Now notice that there's been a little bit of a change to the graph here, the scale in particular. Along the x-axis we've converted to radians. This isn't doing anything special here. It's just a little different here. But notice that I've got pi right here. This is 1, 2, 3, 4, 5. There's 6 little spots, blocks there to get up to pi. So right here is going to be pi over 2. Okay, 1, 2, 3, this is going to be 3 pi over 2. This is just to mark off, in essence, our 90 degrees, our 270 here. Once again, on the vertical scale here, it goes up to 1, so I'm going to mark off the ones that are important, the 1/2, and then the root 3 over 2. And down here, this will be the negative 1/2, the negative root 3 over 2. Now, cosine. We start to plot these points here. Again, we start with the terminal arm on the positive x-axis, so we're starting along here. And we just work our way around here, right? Now think about cosine. Cosine is associated with the x-coordinate here. So at 0 degrees, cosine actually starts at 1. So cosine starts up here. And then as we go from 0 to 90 degrees, or pi over 2, cosine drops in value. So it goes down to there. And then at 90 degrees, or pi over 2 radians, the cosine is 0. Now that was quadrant 1. Now in quadrant 2, between pi over 2 and pi, remember cosine is negative and dropping towards its minimum value of negative 1 at pi. And then after that, once we get into the third quadrant, okay, it's still going negative, but then it comes up to 0, and then once we get to the fourth quadrant, cosine becomes positive again. And then it goes up to its maximum once again when we get down to 2 pi, because 2 pi and 0, remember, are basically the same thing. And now we just connect the dots to get a sense of what cosine looks like. And there we go. There's our cosine graph. Once again, I can break this into 4 quadrants, and you'll notice the cast rule popping out of this. Cosine is positive in quadrants 1 and 4, negative in quadrants 2 and 3. Now, same thing for sine. Sine is positive in quadrants 1 and 2, negative in quadrants 3 and 4. So you can see the cast rule coming out of the graph here. Once again, this can be extended backwards, okay, because these are going to have a domain that's going to be all reals. So that's I'll just do this real quick here. So this can be extended this way. But notice once again that the period, that the cosine graph here repeats at 2 pi radians, or 360 degrees. Basically, once it's gone through all 4 quadrants, this thing repeats. It needs all 4 of these motions for a complete period. Okay. Notice again that it goes in between these 2 lines here, positive 1 and negative 1. But cosine starts at its peak. Cosine starts at a maximum value. Okay, not at the center here. It starts up at a maximum value here. But now, I guess most significantly, notice that shape is almost identical to the sine graph. In fact, the best you can say here is that cosine has actually been translated. It's the sine graph really just translated 90 degrees to the left. Okay, but they are the same graph. That's why even a cosine graph here, this thing right here, is called sinusoidal. Okay, still considered a sinusoidal curve. That's what cosine looks like.
And now y equals the negative cosine of x.
Okay, so finally we're going to take a quick look at negative cosine, but this should come as no surprise to you that the negative is going to cause that vertical reflection here. I'm just going to mark off the values that are important once again. Pi over 2 and 3 pi over 2, and then on my scale here, positive 1/2, then root 3 over 2. Down here, negative 1/2, and then negative root 3 over 2. But when you throw the negative in front here, remember cosine starts at positive 1, so negative cosine is going to start at negative 1, so down here, and then it's just going to work its way in the opposite direction. So in this case here, we should find that cosine is going to be negative in quadrants 1 and 4, and positive in 2 and 3. And that actually bears itself out in the graph. Okay, when I connect the dots, well, I've done better, but anyway, there you go. That's the idea. Okay, and again, it can be broken up into 4 different quadrants. Here's quadrant 1, 2, 3, 4. Okay, 4 different motions. I need all 4 of those. It finishes its run here in 2 pi radians, or 360 degrees. And once again, if I really desperately needed to, I could carry this backwards and keep going, because this thing has a domain that is all reals. And so it's going to extend out in both directions here. Anyway, there you go. Notice again that this is the only graph of the 4 here. Actually, let's look at all 4 here just to show the difference between them. Positive sine, its run through the quadrants here starts, and it's at the center of its motion, vertical motion, starts at the center, goes up. Negative sine starts in the center, but it goes down. Cosine starts at the top, negative cosine starts at the bottom. Okay, you need to be familiar with these. You need to have memorized those positions there so that you can answer a lot of the questions you're going to get asked about this material in this chapter.
Amplitude and period.
All right, now we want to talk about amplitude in addition to period. Amplitude is half of the total height of the function. Okay, half of the total height. So it's how far up the graph goes from the center of its motion here. So if you take a look at, for example, at sine, the reason I point at sine here is because sine is just really easy to notice here. Here's the middle. Okay, it starts on the middle, goes up, come back to the middle, goes down, goes back up. So the question is, from the middle, how far up does it go? And the answer is, for sine, it goes up to 1. Okay, it goes down to -1. The amplitude is the separation from that center, how far we go out from the center. Amplitude is going to be positive by definition, because it doesn't matter whether you're pulling it down or pulling it up, it's the separation here. The equation that we typically do, okay, and we would use the letter A for amplitude. We're going to use the maximum value of the function, we're going to minus the min, and divide by 2. It's the separation between the two, okay? Now, period, okay, is the horizontal length of a cycle. Okay, now there are a few ways you can measure that, and so sometimes it's kind of hard to discuss period. Most of the time it's with respect to time, because the applications that we use in a lot of cases are wave related. So how long does it take a complete wave to pass a certain point, sort of thing. But for our purposes in the graph here, it's going to be the horizontal length of one cycle. Now, for the most part, you've seen that sine and cosine run through a complete cycle as that terminal arm rotates all the way around the circle. Now that's a full 360 degrees, or 2 pi. And I need the full rotation to get a full period. So here we go. For the amplitude of sine, we've seen that it goes up 1. Cosine really produces the same graph, just shifted horizontally, so it also goes up by 1. The period is 360 degrees, or 2 pi, and so is the period for cotangent. Okay, its domain is going to be all reals, and so is, did I say cotangent? I meant cosine. I think I said cotangent. I meant cosine there. Sine and cosine, both going to have domains that are all reals. The range, okay, is going to go from -1 to 1. And so it'll do the same thing for cosine. Now, we've already talked about this in some detail in previous lessons here. This quality right here is unique to these two. There is no other trig function that has those particular properties here, which is, by the way, why sine and cosine are really what we would consider our primary trig ratios. Everything else is built up from those two guys. Because the values are kept within this very, very limited range. Okay, -1 up to +1. All the other trig functions will extend out to infinity at some point here. So these things are kept in a very, very tight little band, which makes them easier to work with. This right here, everybody, these are the basic properties of those two sinusoidal functions.
The characteristics of a sine x and a cosine x.
So now what you need to know here is that when we talk about sine of x or cosine of x, these are just functions. Okay, they're just functions of x. Granted, they're trigonometric functions, but they're still just functions. And so when we put an a in front of that, really, this is like a times f of x. And so now let's just think back. What happens when you plug an a in front of a function, or a constant in front of a function? What role does that function serve? Well, it serves to be a vertical stretch. And so that's
Y equals 3 sine x.
Now, we know that sine of x, if we do this here, if we make this our scale here, 1, -1, -2, -3, 2, 3. Okay, sine all on its lonesome would do something like this. It would start here, goes to a half, up there, to a half, down, -1/2. Whoops, sorry, -1/2. That is not -1/2. This is sine. Okay, so this is your sine function. Now, 3 times sine is simply going to be a vertical stretch by a factor of 3. Now, that's not going to affect these guys right here. These will be invariant points because they are on the x-axis. The y-coordinate is 0. However, something like this point right here is going to go 3 times higher. This point right here will be 3 times lower here, okay? Because everything gets stretched away from, away from the x-axis. Now, this point right here that was half initially is going to go to 1.5, and that's this one's going to go up to here 1.5 here, and then this will come down to negative 1.5. So where are we at here? Negative 1 right there, and then up to there. Now, I don't really have to do the rest of it here just to get a sense of what's going on. Just got to connect the dots, and so this is our function right here. Okay. Now, what was the amplitude? Well, the amplitude. Notice originally that the distance from the center to the top was 1. Now that has been stretched by a factor of 3. Because remember that a stretch stretches the distance that an object is from the axis. Okay? It stretches the distance from the axis. Now amplitude is the distance from, if you're just talking about sine, cosine, tan, sine and cosine, not tangent, but sine and cosine, it's just the distance from the axis, the x-axis, to the top there, to the peak or to the bottom there. So this is now going to be stretched by a factor of 3. This was a vertical transformation, so it had no bearing on the period. The period is still 360. The domain is still going to be x is an element of the reals. Okay, but our range will change because it used to be negative 1 up to positive 1, and now it's going to be negative 3 out to 3.
Y equals negative 2 cosine x.
Okay, so first of all, again, notice that we've got this stretch factor here, but also we've got the negative here, and that causes that reflection. So we're talking about negative cosine. You might even want to think of it like this, because we already know what negative cosine looks like. This would be 2 times negative cosine of x. You could think of it like that if you wanted. Negative cosine, okay, if you will, remember this is going to be pi over 2 here. This will be 3 pi over 2. In this case here, we can simplify things just a little bit here. Let's make this 1. We'll make this negative 1. So this is going to be 2. Down here will be negative 2. So cosine, a regular negative cosine is going to start here at the bottom. Okay, it's going to get to 0 at pi over 2. At pi will be up to 1. 3 pi over 2 down here, and then 2 pi will be down here. And so just a regular negative cosine is going to look something like that. Okay. Now, if we stretch this vertically by a factor of 2, these points here won't change, but these distances here will. Okay, the distance of 1, this distance of 1 is going to stretch and become a distance of 2, and this is going to become a distance of 2 as well. So our negative 2 cosine is going to start down here at negative 2. It's going to come up to 0, up to 2, through 3 pi over 2, and then down to negative 2. And so this piece right here, this is our y equals negative 2 cosine of x. Notice it's maybe a little bit hard to differentiate, but yeah, it's that larger one there. And as I pointed out a couple seconds ago, the amplitude here for just a regular negative cosine is 1, because the distance from that axis up to that maximum point there is just 1. That's been stretched to 2, so the amplitude is 2. So we should be noticing now that the amplitude is going to be essentially the same as the vertical stretch here. This was a horizontal transformation, so nothing really happened to the period. The period is still 2 pi. The domain is still element of the reals, but now the range, instead of going from negative 1 to 1, this goes from negative 2 out to 2.
The characteristics of the sine of bx or the cosine of bx.
All right, so now in this case right here, once again, the way you got to approach this is to think about sine and cosine as functions acting on x. And so now we've got the sine of bx, the cosine of bx. This is going to be similar to y equals f of bx. And if you think back to the transformations chapter, this right here is a horizontal stretch by a factor, okay, of 1 over b. Okay, by a factor of 1 over b. Now, that's a horizontal stretch here. Now let's think about what's going on. Sine and cosine both have these infinite domains. Okay, so horizontally stretching these things, I mean, it isn't going to change the domain, but there is a characteristic of these two functions here that is defined along the domain, and that's the period. So really what this means is we're going to stretch the period, okay, by 1 over b. That's really what's going on here. Now, normally, so for example, if normally you would expect there to be one period between 0 and 2 pi, okay, or 0 and 360. If you plug a 2 in for b here, that's a horizontal stretch by a factor of a half. So now it's half as big. So what happens here is in the period is now half as long as it should be. It was stretched by a factor of a half. So now 360 becomes 180. But what that means is between 0 and 360, now you've got two of them. Okay? You've got two different functions here. So what happens here is b also becomes, I'll maybe write this up here, b is the number of periods between 0 and, let's say, 360. Okay? In essence here, if you want to give it a characteristic, you can call b the frequency of this graph now. Okay?
Y equals the sine of 2x.
All right, so now we can see inside this function we've got the 2x here. What I'm going to do to start off with here is I'm just going to draw a regular sine graph, okay? So I'm going to make this up to 1, and we'll make this down to, wait a second, what I got, 1, 2, 3, 4, yeah, we'll go down to -1 here. I'm just going to draw a regular sine graph. So it's going to go from here, it'll hit its maximum at 90, back down to 0, down to 270, and back up to 0 here. So now I'm not going to do anything too terribly fancy. Actually, maybe what I'll do here is, what is this? It'll go up to here. No, that's not true. 1, 2, 3, 4, 5. So it's going to be right there. So it'll be something like this. Where are we at here? Something like that. So coming down. Anyway, you get the idea. Something like that. It's not very good, but you get the idea. Now, sine of 2x means that there's been a horizontal stretch by a factor of a half. So that means all of these points here, okay, the distance away from the y-axis is going to be cut by a half here. So now this point right here is going to go to here. The point at 180 is going to drop down to 90. The point at 270, okay, well, I got to count this out here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's going to be 4.5. So 1, 2, 3, 4. Okay, little squares there. It's going to drop down to here. And then 360 is going to drop down to 180. So this thing's going to actually start going to look like this. It's going to be much tighter here, okay? And you got to think about the way that works here. The function sine is still running through all four quadrants. It's just that every time you plug an angle in for x, okay, the 2x doubles it. So when you plug in, for example, 90 in for x, the sine sees 180. Okay, when you plug 45 in for x, the sine is seeing 90 because the 2 doubles it before sine gets to it. And that's why it's going through your four quadrants a lot quicker. Now, additionally, what that means is that we're going to get, in fact, I'll extend this thing out here so that you can see the whole thing. This is going to now give us between 0 and 360, where there used to be one period, now we're going to have two periods. And so right here, this is our y equals sine of 2x. Now our amplitude has not changed. Okay, the distance from the axis up here to the maximum, or the center line here, if you will, to the minimum to maximum is still 1. My period, though, has changed. Okay, the period here, okay, was 360 degrees, but now I'm essentially multiplying it by 1 over 2. I'm stretching it by a factor of 1 over 2. So this becomes 180. The domain, however, is still all real numbers, and the range, again, what we just saw there was a vertical transformation. So the range, a horizontal transformation. So the range is still -1 to 1.
Y equals the cosine of 1/2 x.
All right, now we've got a slightly different sort of stretch factor here. Now, once again, I'm going to draw out cosine, just a regular cosine here. So here's pi over 2, here's 3 pi over 2. What it will do is I'll make this, again, this is 1 down here to -1. So cosine starts at its peak right here. It's going to go down to 0 at pi over 2. It's going to go down to -1 at pi, up to 0 at 3 pi over 2, back up to 1 at 2 pi. Now, this right here is giving us a horizontal stretch by a factor of 2. Okay? Now, what that means here is that all of these distances that these points are from the y-axis is going to double. Now, this one right here is going to stay the same. That's going to be an invariant point. But this one here at pi over 2 is going to go to pi. Okay? This one here that was at pi, this point down here is going to jump up to 2 pi. And actually, that already pushes me off of my grid here. And so what this looks like is it's going to come from here. It's going to slide down to here. And it's going to come down to there. And so really all I'm getting between 0 and 2 pi is I'm only getting half of a period. Okay. So really that number inside there, that coefficient of the x there, is the number of periods you can expect now between 0 and 2 pi. Now I can use that to figure out what the period is, but anyway, so just to identify this graph right here, this is my cosine of 1/2 x. My amplitude is still 1. That hasn't changed anything. This time though, my period, okay, I took the 2 pi and I'm stretching it by a factor of 2. I'm dividing by a half here essentially, right? Okay, because you're multiplying by the reciprocal and then this becomes 4 pi. So this is actually twice as big as it used to be. My domain, still all reals, and my range hasn't changed because this was a horizontal transformation, not a vertical transformation.
A quick summary.
So right here's a quick summary of what we've been looking at. So now this graph right here that we're looking at, this is a cosine graph, okay? And I can tell it because I'm starting at the peak on the y-axis and then down I go. So here are my 4 quadrants. This is my period, okay? The horizontally, the length of the piece that gets repeated, okay? And there's got to be these 4 motions to it, from the top to the middle, middle to the bottom, middle to the, bottom to the middle, middle to the top. There's always going to be those 4 motions in a period on a sinusoidal graph. So if you're ever stuck trying to figure out what the period is, just remember there's 4 motions, okay? Again, top to middle, middle to bottom, bottom to middle, middle to top. And now you can put those in slightly different orders if it's a sine graph, but that's how that works. If you want to figure out the relationship between the period and that b value, okay, what's been the frequency here, period is going to be 2 pi if you're in radians over the absolute value of b. Now the reason why we say the absolute value of b is because there could be a horizontal reflection here, but when I talk about period, I don't really care about that. Okay, that negative there is just irrelevant. So don't worry about the negative there. Just divide by that value here. And if you're in degrees, you would just divide by the absolute value of b. So that's how you get your period out of that. If you ever wanted to get b, like if you were looking for that stretch factor, that would just be 2 pi divided by the period. And because of the way you would do that, this would always be positive, right? You wouldn't throw in a negative for the period there to get a negative b value. So you would just automatically get the positive value. Okay? Notice that without a transformation here, the maximum value should be 1, the minimum value should be 1, and then your amplitude is always going to be, okay, half of the difference between the max and the min. That's a formula there that you should memorize. Okay, it's not going to show up on your formula sheet, but man, is that ever useful when you need it.
Complete the following table.
Okay, so in this case right here, we're going to identify the amplitude and period. Now, essentially what we're doing here is identifying the vertical stretch, and this isn't exactly true, but it's sort of the horizontal stretch. Now we're going to apply the horizontal stretch to the period to get the new period, but this is essentially what we're doing here, the 2 ideas that we're pulling out of this. Now, if you've got a sine function here that doesn't have any kind of transformation, the amplitude is 1, the period will be 360 degrees. Okay? That will be true for cosine as well, without a transformation. So now let's take a look at it. This has had a vertical stretch by a factor of 2. That means its new amplitude is 2. There's been no horizontal stretch or whatever, so the period is still going to be 360. Here, remember the vertical stretch would come in front here. Since there's nothing there, I assume that the number there is 1. So the amplitude here is going to be 1. This time, there's been a vertical stretch right here, okay, vertical stretch by a factor of a half. So instead of being 360, this is going to be 180. That's my new period there. Here, okay, notice that the coefficient here is -3. Now the negative simply means that we're not talking about your regular sine graph, we're talking about one that's been reflected. Okay, so don't worry about that. This just means we're not talking specifically about sine. This is now negative sine. The value here of the stretch is the 3. A stretch factor can't be negative. Okay, that's a reflection. This is the stretch factor. So it's been vertically stretched by a factor of 3. Okay. Oh, I can't believe I did that. That's not a vertical stretch by a factor of 3. My mistake. So I just noticed that. Sorry about that. That was a horizontal stretch. Ooh, sorry. Embarrassed. This is a vertical stretch by a factor of 3, which means my amplitude will go to 3. Because nothing's happened horizontally, okay, the period is 360. Here, now I will get this one right this time. This right here is a horizontal stretch by a factor of, and we take the reciprocal of that, 1/3. Okay, so I expect that between 0 and 360, I'm going to get 3 periods there, because each one of them is now 1/3 the size here. There's been no vertical stretch, so this has got an amplitude of 1 still. And now I take the 360 and divide it by 3, and I'm going to get a period of 120. So this function right here is going to be able to run through, okay, all 4 quadrants in 120 degrees. Okay, because by the time you plug 120 into this, the calculator will see that angle as if it was 360, because it multiplies by 3 first. Here, we've had a vertical stretch by a factor of 5. So that's going to make my amplitude 5, and this has had a horizontal stretch by a factor of, 1/4. Okay, well 1/4 of 360 degrees, because now what that means is you're going to have 4 periods between 0 and 360. So each one of them is 1/4 that size. It's going to be 90 degrees. In this last one here, I've had a vertical stretch by a factor of 1/3. Okay, that means my amplitude is going to be 1/3. And I've had a horizontal stretch by a factor of, in this case, 2. So now instead of, so what's happening here is I've actually only got, between 0 and 360, I'm only going to have half of a period showing up. So the other half is going to be in another 360 degrees. That means my full period will be 720 degrees. Okay, and I hope that made sense.
State the period in radians and the amplitude of each trigonometric function.
Okay, well, when we take a quick look at this, let's look at the period first. A period has to have 4 motions. Now, this appears to be evenly kind of distributed over the x-axis here. So the middle here must be on the x-axis. So here's my period here. From the middle to the top, top to the middle, middle to the bottom, bottom to the middle. So there's my 4 motions. There's my period. The answer is 2 pi. Okay, from 0 out to 2 pi. There's the full period. The amplitude is the distance from the center, okay, which in this case is the x-axis. Nothing's been moved yet, so it's still the x-axis. It's the distance from the center to the top or the center to the bottom. Now in this case here, I can just read that off. It's going to be 0.5. If you don't like that, okay, if you don't like kind of thinking it like that, you can always use that formula. The maximum value here is going to be 0.5. The minimum is -0.5, and then if you divide that by 2, so 0.5 minus -0.5 is going to be 1. Divided by 2 will be 1/2 or 0.5, and there's another way of getting the amplitude. All right, so let's take a look, when we look at this one, let's look at the period first. So again, notice that the graph appears to be fairly evenly distributed over the x-axis, so the x must be the middle here. And I'm going to start on the y-axis here. I've got this motion here from the top to the middle, middle to the bottom, bottom to the middle, middle to the top. There's my 4 motions. There's the 4 quadrants right there. Where does it end? It ends at 2 pi over 3. Okay? Now, another way of doing that, if you wanted here, would be to take a look at this. Here's 0, here's 2 pi. Now, from 0 to 2 pi, I've got 1, 2, 3 periods. So that means each period, okay, 2 pi, I've got 3 of them in there. I'm basically dividing 2 pi into thirds. There's my period. That's got to be the size of each one of those periods there. Now the amplitude, again, looking at the center value here and then just kind of mapping out the way it moves away from the center value here, how far it goes. It goes up to 1, down to -1. Or I could do my formula here, the maximum minus the minimum over 2. But no matter how you kind of read it off here, it's 1. The distance from the center of this motion to the top or the center of the motion to the bottom is just 1 unit. Okay, now remember, this is not the distance from the top to the bottom. That distance is twice the amplitude. That's why when you take that difference there, you have to divide by 2. Okay, now this question here requires a little bit of faith on your part here. Notice I've given you this kind of big bump here. You're not even seeing a full period. I am seeing, now this is the faith part here. I have to assume that what I'm seeing here is half the period. Okay? Now that is a safe assumption because we're not trying to trick anybody with this. Okay? So when you see something like this, your first instinct on this would be, well, that looks like just the top half of it. Yeah. Trust that that's true. Okay, that's correct here. So to go from here to here, this is what from the middle to the top, top to the middle, half the period, and that's 3 pi. That means the bottom half of this period, if you were to keep drawing this out here, would be another 3 pi. So the total period here has got to be 6 pi. Has to be. Now, the amplitude, again, because I'm assuming that this is in fact half of a period, the amplitude here is going to be the distance from the center here to the top. This is my amplitude, and I can read that right off the graph here. That's 1.5. Okay, now I can't read off what the minimum is. It's harder to use the formula here because I do have to assume that the minimum is negative 1.5. And again, that would be a safe assumption here, but I think in this case it's easier just to note that this is 0, this is 1.5, that distance there is going to be just 1.5, and there's my amplitude.
Write the equation of each of the following. A sine function having an amplitude of 2/3 and a period of pi over 6.
Okay, well let's pick the low-hanging fruit here first. The amplitude is 2/3. Okay, we've already seen enough here to know that that means when I write my sine function as y equals a sine of bx, I already know that the a here has got to be 2/3. Okay, that's the easy part here. My period, though, is pi over 6. Okay, now we know that period, and bear in mind that if my period is pi over 6, I'm in radians. So that period is 2 pi over the value of b. Now, I can multiply this through by b and then divide by p to get b is equal to 2 pi over p. Okay, and so now I can plug stuff in here. So 2 pi divided by, well, my period was pi over 6. Okay, the pi's will cancel, and when you divide by this 1 over 6, you're going to multiply by the reciprocal. I'm going to get that b is equal to 12. Okay, so now I know what a is, I know what b is, I simply have to plug this in, and I will get y is equal to 2/3 sine of 12x. That's the equation that we're looking for.
A cosine function having an amplitude of 3 and a period of 720 degrees.
All right, and same with this question right here. First thing I'm going to do is identify what the significance of the amplitude. Now I'm looking for a cosine function, so y is going to equal a cosine of bx. But when I'm told the amplitude is 3, I know that there's been a vertical stretch by a factor of 3. That's the easy part. Now, period, and notice we're in degrees because I'm giving you that the period was 720 degrees. This is going to be 360 over the b value. And just like we did in the previous question, I can multiply this little expression by b, divide by p. So b is equal to 360 over p, the period. Okay. And that means, sorry, I don't know why I'm writing p again there. It's weird. B is going to equal 360 degrees over 720. And that means b is equal to a half. And so there we go. So now I know a is 3, I know b is a half. Now it's just a matter of putting that information in. So y is equal to 3 cosine of 1/2 x. There you go.
The tangent function.
All right, everybody, we're going to take a few minutes here now and we're going to talk about the tangent function. Now, before we get into this information right here, I want to just draw your attention here real close to the unit circle. And we'll zoom in on this. Here's our unit circle, okay? So we've got the point here 1, 0, 0, 1, negative 1, 0, 0, negative 1. Okay, now tangent, okay, tangent is going to be positive here and here. It's going to be negative here and here. Okay, tangent is the y-coordinate divided by the x-coordinate. So that's going to go from 0 over 1, so it's going to go from 0 to 1 over 0, undefined. Okay, then it's going to go from this undefined to 0 down to undefined again. Now, notice what's going on here. It's, okay, from here, it's going to go from undefined to 0 to undefined through a negative quadrant, through a positive quadrant. Then it's going to go from undefined to 0 to undefined through a negative quadrant, through a positive quadrant. Tangent is completely repeating itself. It's the exact same thing here as it is here. Okay? In essence here, this is the period, okay, of tangent. Tangent repeats only on the half of the circle, not the full circle, not like cosine and sine. And in fact, when you come up to our graph here, okay, I'll zoom up just a little bit. Okay, I know that's going to be undefined here at negative 90. So 1, 2, 3. So right here, negative 90, 1, 2, 3, right here. And so the graph here is actually going to have an asymptote. Tangent, okay, is undefined at 90, undefined at negative 90. It's also going to be undefined at 1, 2, 3, 270. Okay, basically, as soon as the coterminal arm is on the vertical axis, it's going to be undefined. 1, 2, 3, so it's going to be undefined here. And now, tangent sort of looks like this. Okay, at 0, it's 0. We identified on our unit circle here that at 0, it's 0. At 180, it's going to be 0. So we know that it's going to go through these points right here. And it's going to, at 360, it'll be the same thing. And then what it does here, between 0 and 90 is its first quadrant. And what we know is tangent increases up to infinity. In the second quadrant, okay, sorry, if you go backwards into the fourth quadrant, kind of rotate this way. It was undefined here, it's undefined here, but in this case it's negative. So what's happening here, this represents the fourth quadrant. Remember, negative 90 to 0, negative 90 to 0. This thing actually swoops down to negative infinity. That is what a period of tangent looks like. Now it's a little better than that. My graph's not great here, but that's the idea. And then this is what repeats over and over again. So now this one up here, I've only got to there. Over here, it's going to come up. Oh, that was terrible. Hold on. Fix that to 180 through up to there. That was bad too, but anyway, and there you go. Okay, that's what the graph of tangent roughly looks like. Okay, and again, reiterate that the period here is just 180 degrees or pi radians. So now let's take a quick look at these properties over here. You'll notice this first one here, that it has a period of pi or 180, so b is equal to pi over the period, or b is equal to 180, okay, over the period. Or other way around if you wanted to, okay, if you want to say it this way, P, the period, is going to be equal to pi over B or 180 degrees over B. Either way, one of the things you got to memorize here is that the period of tangent is smaller than that of sine and cosine. It's 180. We've also got discontinuities, okay? It's undefined at pi over 2, 3 pi over 2, 5 pi over 2. In other words, to shorten that up here, it's just this right here. It's undefined at 90 degrees or pi over 2 radians, and then it's going to be undefined every 180 degrees or every pi radians beyond that, every step of pi, because that's the period. So if you've got one undefined value at pi over 2, the period is pi. That undefined is going to repeat every pi radians here. And those discontinuities, okay, or places where it's undefined, translate into vertical asymptotes, which you saw when I graphed that. Okay, those dotted lines there are the vertical asymptotes that it approaches here. It's going to have x-intercepts, okay, at basically multiples of pi, okay. And then their domain here is going to reflect what we saw with the discontinuities, okay. Basically, to identify the domain of tangent, you're going to identify where their problems exist, and the problems exist at those vertical asymptotes. And really importantly, don't let them throw you off with this one. It has no maximum or minimum values. Okay, therefore, it has no amplitude. You can't use the idea of an amplitude to discuss a tangent function because it just doesn't make any sense. Okay, the tangent moves up infinitely and down infinitely. Okay, the range, like it says here, is all reals. And there's tangent. Now, you'll notice we're not going to do much more with this. We will do a little bit as we go through the assignments here, but we're not going to ask you much on tangent. The focus of this course is going to be on sine and cosine.